Okay, so this video, to all the subscribers, if you see this thing pop up, you might have already seen this video, measuring small things. By popular demand or just total embarrassment, I'm going to go ahead and fix up the numbers. Had a lot of pointers, complaints, whatever you want to call it, that I did the math wrong. And I did. I absolutely screwed up on some of my conversions. So I'm going to fix up all the titles and repost this thing. And that'll be my work for today, at least in the editing. So here you go. Okay, today's video, what we're going to do is take a deep dive into measuring. Adam Savage has a wonderful, Adam Savage from Mythbusters, he has a wonderful video on gauge blocks, mostly gauge blocks, measuring in general. I don't want to repeat a lot of what he's done because his video is awesome. I'll include a link in that in the description, but we're just going to go over what I use here to measure and the accuracies that we deal with here on some things. Of course, the very first thing is a tape measure. A lot of times what we'll use a tape measure for is just getting material squared up, rough cut, into shape. I leave plenty of material on with a tape measure measurement. You can only be so accurate with this. Probably a 32nd of an inch. Each graduation on this guy, if I hold this correctly, each graduation on this guy is 1/16 of an inch. So you could do half of a 16th fairly accurately. Is it necessary with this? I don't think so. I just use this as rough measurement. So the next thing that I would use for measurement would be a scale. This is not a ruler, this is a scale. This particular one is 12 inches long. It is divided up into 32nds of an inch, 64ths of an inch, and then if I flip it over, I also have tenths and 100ths of an inch. So very, very handy. Every machinist has multiple scales. I have some that are shorter, longer, in metric, in inch, in hundredths, in tenths, all over the place. This one's a General, made by General, stainless steel. It's probably 30 years old. I've had it forever. So that's a scale. The next thing that you'll move up to, and all machinists have calipers. 6-inch would be the standard that everyone has, but I've kind of migrated away from the 6, and I really like an 8-inch. And this is Mitutoyo. This is coolant proof. I really like these because if you leave them sit for a little while, inactivity will shut off the display. The battery in this thing lasts almost forever. Very nice. And the accuracy of a set of calipers is about 1,000th. Now these guys will read half of 1,000th, but you do not want to rely on anything down in the 5/10,000ths of a range on a set of calipers. That would be a no-no. I'd say 1,000 is what these are good for. Now, if you want to get down past 1,000th, 1,000th, you're going to need one of these. This is a micrometer. This particular one is inch. It is 0 to 1 inch is its measurement range, and this guy is probably also about 30 to 40 years old. It's also Mitutoyo. For the newbies who do not know how to read one of these guys, I've got a 16 millimeter gauge block in here, and I will go over that later. This is very, very accurate 16 millimeters. And you can see here that what we have is, this is inch. Remember, this is a 0 to 1 inch micrometer. And what we show is this is 0.6. And then I can see the very first hash mark, which is 0.025. So we're 0.625. We don't quite make it to the to the next 5, 4, we're in 4 and then some, so it's 0.625 plus 4, 29, 0.629 is what this is. And then what we do is we come over here, and back here we've got 0, 1, 2, 3. You see which one on the dial lines up with which mark on the body, and that's all the way down to the 9. We don't make it to the 0, we make it to the 9. So this measurement right here is 0.6299. So this is pretty darn accurate to 4 decimal places. Just as a check, we take that same gauge block and we take our calipers, see where we're at. You know, it's as close as these things are going to get. Okay, the next thing I have in the accuracy department, the next best thing, here's a 0 to 1 inch Mitutoyo digital. Now you can see this guy is good to tenths, hundredths, thousandths, 10,000ths, 500,000ths, or half of a 10,000th. Is it repeatable? Is it accurate down there? Remains to be seen. Depends on the weather conditions, humidity and temperature, various things, how you're using it. But I've found good repeatability in these guys. So let's see what our the same 16 millimeter gauge block, what it measures in these guys. Okay. So what you want to do is twist this. This is a ratchet. This is kind of like a clutch. It gives a little bit. You don't want to grab this and crank it down until the measurement you get, you know. You can affect it any way you want, but you can see right there, 0.6299. Exactly the same thing that we achieved with the old school vernier style micrometer. So the neat thing about these guys is that I can actually transfer this to millimeters just by the push of a button. So there you go. I mean 16.01. I think that relaxed on me just a little bit. There it is. 16. Now all of these guys, whether it's the old school one or the new school one, they all come with a reference, and this particular reference is 1 inch long. I don't know if we can see that, but right there, 1 inch long. So all you do is just open this guy up. Stick him in there. There you go. That's pretty darn tight in there. Okay, similar to the little reference piece we use to kind of calibrate our micrometer. Similar to that, we also have various other ways to either measure or space things to very, very accurate distances. I have a set of dowel pins that are gauge pins, so they vary in length or they vary in diameter from extremely small, the size of a needle, all the way up to about 1/2 inch. Several kits of those. I think I showed it in the last video. We also have this, and this here is a set of gauge blocks, and this particular set is steel, and it is a grade 2, probably about 30 years old. Nowadays, this set of gauge blocks costs about $2,000. Again, Mitutoyo. You can buy them much cheaper, lower cost, but this is good quality. You open it up and there's some anti-rust absorbing kind of paper, and then the gauge blocks. Again, these things are very old. They've been around way longer than I've been here, and we're missing a couple, but the way this is set up, you can basically you can make any size you need given these guys right here, down to its level of accuracy. A little Google search, and you can see right here there are 4 tolerance grades of gauge blocks. There's 0.5, 1, 2, and 3. Now I have the 2 series, 2 grade, and it says that 0.5 and 1 are usually used as calibration masters. 2 and 3 are of lower quality and used for measurement and gauging purposes. So basically I have grade 2, and that would be the best thing that you would use for measurement and gauging purposes in a normal application. Now you can buy, if you watch the Adam Savage video, he has given to him by Mitutoyo, I believe, no, Starrett, given to him by Starrett. He has a set of ceramics, and you can kind of see the price. It's this set of ceramics at MSC is $8,500. Okay, so we're doing the deep dive into size and measurements. So let's cover tolerancing. The type of tolerance that I typically work with is 0.0005. Now, that's half of 1,000th. How big is 1,000th? Well, if you take a sheet of notebook paper, or copy paper in this case, a typical sheet of notebook paper or copy paper is going to measure 4 to 5 thousandths. So this particular one is 4.5. There is 4.5. We'll measure multiple spots on this piece of paper. Whoops, sorry. And yeah, so 4.5 thou. 4 to 5 thou. Now, if my typical measurement is that I hit is half of 1 thou, well, you know, that's significantly more accurate than the thickness of a piece of notebook paper, right? Okay, so now we're talking about crazy numbers. Past a half of 1,000th, my ability to measure things accurately. Now, granted, I can measure things down to, about 3 microns. What is a micron? Okay, micron, the metric measurement equivalent in inches. Now that's about 0.0002. I can get pretty accurate down there. Fairly repeatable, and it's something I can measure. Can I hit it every time? Usually, but it takes a lot of effort. So 3 microns is essentially, if you were to take that piece of notebook paper and take a slice the hard way down this thing and divide this into 20 different sheets. That's what we're talking about there. Okay, now we've covered microns. So the next thing that we're going to go down to with these gauge blocks is a known quantity. And that known quantity is going to be nanometers. How big is a nanometer? Okay, a nanometer is 0.0000001 of an inch. Okay, very small, very small. So these gauge blocks are designed to be stacked up. Let's take the 16 and the 17, the same one we were using earlier, and the next size bigger. Say you wanted to stack these things together to achieve a measurement, or a reference, or a stack of material that would space something at a very specific height. What is the difference? What is the difference between this surface and this surface when they are together? So now you can see the level of quality that we're dealing with here. They are mirror. These are lapped to the point where that is a mirror surface. Okay. So when I put these two together, what's the space between them? Is it 0? It is not. Air exists between them that you cannot get out, okay? Now these are not magnetic in any way. They're completely dry. I have put no oil on them. No grease, no oil, no adhesive, nothing like that. Now the process to get a known quantity, and that known quantity is 25 nanometers of space between these two. The process is called ringing. So the way you put these guys together is just like this. To put these guys together, apply good pressure and twist. And look at that. It's essentially a vacuum. It's in debate on what holds these things together, whether it's vacuum or I really don't know. But in this case, what's holding these together, whatever it may be, which is in debate, we do know that that gap, that space between them, is 25 nanometers. All right? So that is the smallest measurement that I could possibly deal with on a daily basis. All right. Here you can see those blocks rung together. I don't want to drop this guy, have him fall off, but I mean, that guy's on there, right? The only thing holding it is essentially me ringing them together. There they are. No magnetism whatsoever. Right there. I don't even have the full surface together. "25 nanometers. All right, so why would I want to stick two of these guys together? Well, just one possibility would include this. Let's get this out of the way and bring this guy in. This is a sine bar. Now, to my knowledge, sine bars come in two different sizes, commonly. This one right here, you can see from the center of this round thing, the pivot point, to the center of this guy here is 5-inch. Maybe this will be more visible. We go from here to here. So it's a 5-inch sine bar. Now, this is basically got a flat right here that allows some spacer you put in here to come in contact with the bottom of this. This is essentially a triangle. You know one length, so it's pretty easy. This is a 90, so it's pretty easy to come up with this height. It's just trig. Now, in the Machinist Handbook, there is a whole section on this. The new one here, the newer one here, you can see sine bar. The newer one does not have the columns and rows of cheat sheets that my old one used to have. But we know that's all available online. But nonetheless, this is super common in a 5-inch and a 10-inch sine bar. We use a stack of gauge blocks to achieve the height, which will determine the angle. Simple trig. And then what we do is, whatever that angle requires, we take our stack, we put it in here, we loosen these guys up and let this guy down, and that will produce an extremely accurate angle, down to parts of a minute. And of course, we're dealing with degrees, so if it's a compound angle, things can get a little fussy. and degrees are important, minutes are important, parts of minutes are important. That would be seconds. So we're able to hit that pretty accurately with just a simple tool like this. Okay, we've talked about what you can get with a tape measure. We've talked about what you can get with a scale. We've gone on to the calipers. We've gone on to the micrometers. Now, smallest number that I can work with in any sort of reliable and consistent manner is going to be about 2 or 3 microns, and we've even gone farther, and we've been able to show exactly what 25 nanometers is. And at this particular place, at this telescope, we also deal, let me show you, what we also deal with on a not frequent basis is a unit of measurement called an angstrom. Now, an angstrom is essentially a unit that is the measurement of the wavelength of visible light. So it is also the atomic radii of phosphorus, sulfur, and chlorine. It's about 1 angstrom. Now, how big is an angstrom? An angstrom is 0.1 nanometer. So let's figure that out. Okay, so here what we see is this is every few years we have to take the mirror out, strip the reflective surface, which is aluminum, and reapply a new reflective surface. And we need to know within a certain level of accuracy how thick was that coating. And what we use is an interferometer. And I'm not going to go into a deep dive on what an interferometer is, but essentially what we do is we do a witness sample, a small piece of glass, right along with a giant mirror. And then what we do is we tape essentially a razor blade to one portion of that. So we have coating and no coating underneath the razor blade. And then what we do is we use an interferometer to look at and see what this shift is between the two different heights. And here you can see what this looks like in the interferometer. One side is with coating, one side is without coating. And the line runs right down the middle. And basically what we do is we measure the offset, and that tells us how many angstroms thick that coating is. And in this case, our average thickness is about 1,128 angstroms thick. And remember, we said that visible light has a wavelength in the range of 4,000 to 7,000 angstroms. So essentially what we're saying when we say that coating is as thick as 1,128 angstroms, now that is not the size of the wavelength of visible light. This is tiny, tiny, tiny. And of course, when I was asking the guys, how accurate is this? Because everything has a tolerance, right? They said that within a reasonable amount of assuredness, this is pretty accurate, probably on the order of something like 20 to 50 angstroms. That could be your deviation. The light that you use to get this data has to be very accurate, and they use a process of a given light source going through a filter. Of course, the given light source could have variances in it. The filter has production tolerances, so you can see where everything stacks up. The smaller you get in these angstroms, or even nanometers, the smaller you get, the harder it is to achieve a tight tolerance. Okay, so we've covered a way to, to linearly measure something. There's another type of measurement device I have, and if you've watched any of my other videos, you've seen me occasionally from time to time use this guy up on, say, the quill of a Bridgeport or of the CNC machine, and what I use this for is to sweep something around, and that will tell me where the center of it is. Now, this is an indicator. This particular one, it's quite nice. Interrapid, this is the one that everybody wants. And this particular one, each graduation on the dial here, you can see there's 0. Each notch on the dial is 0.0005. And that is the tolerance that I typically work in. Moves fast. Does not take much movement. So that's an indicator, a dial indicator. I have several different styles and many of them. This particular one, each graduation is 1 thou, and it has 1 inch of travel, you can see there. It's made by Fowler. And here's an oldie. This is a Starrett. And again, each graduation is 0.0005. This has a 1/8 inch range, but interestingly enough, this one goes plus and minus. So if you set this up, here, you can measure negative or positive. I also have digital. This guy is old, but quite nice. And I can output the measurements and collect everything in an Excel spreadsheet. This is not incredibly accurate, this particular one, but it is repeatable, and this is a fine instrument right here. I have 2 or 3 of these. Okay, if you followed the channel, here's the 3D taster. This is very similar to a dial indicator. It just works on a little bit different way. And basically, the ball on the end of this guy down here is 200 thou in diameter. So I've set this at -100, and basically when I come over and hit something and then run it in 100 thou, I know that edge is 0. So that's how that works. And the radial exactness, they call it, of this guy is 0.0004 inches. So you can see this guy will measure more accurately than that, but that is what they will guarantee its repeatability and exactness is. Everything has a compromise. Every measurement has a compromise, no matter how far down you go, even to the angstrom level. So what I'm going to go ahead and do is I'll, like I said in the comments, I will attach a link to the Gauge Block Handbook. It's really interesting, and I think it's a good read. Everybody should read it. Adam from Mythbusters did a whole big piece on this. I'll also include a link to his video, which I would recommend to anybody. I'm basically copying it for my own benefit, but I think it's important information, and I tried to do a little bit deeper dive and much more specific to what I do. I hope it was informative, and stay tuned. We'll continue on.